here, give you an overview of what that means. What is open source? What are the products? And why does the industry care? We first have Jeff Bonwick here, who's a distinguished engineer and also co-creator of ZFS. It's a technology you're probably all familiar with. We have Mike Shapiro.
Oh, you want the lights?
Maybe do that. You can open that one.
No, that one's going to be worse on the screen.
What do you mean?
That's okay, go ahead.
We have Mike Shapiro. Actually, he was distinguished engineer and runs our Fishworks project that he'll be talking about shortly. Michael Cornwell, who's our architect for our Flash and our solid-state disk business, and then our customer here, Mark Majelski of rstage.com. So we'll run through slides. If you guys have questions along the way, jump in. We'll have a kind of a formal Q&A at the end. But if things don't make sense along the way, just very free flow conversation here. Coffee there, water out there. Let us know if you need anything. And with that, we'll have you kick us off. Just give me move on. I'll give you the.
So let's start with this, because you've all seen so many damn presentations, haven't we? And you wonder, where's the up switch for this screen, or is it just a manual? You know?
Oh,
is this just manual?
You know what? It's manual.
Okay. I don't think it is.
Oh, you were trying to put it up.
Oh, here it is.
Oh, okay. Okay.
We're talking a little bit about the election before folks got here, and speculating on why there's been so much media response to the Sarah Palin thing. And I think it's really very simple, which is we're all just so tired of the other ones. Something new to talk about. So let's not go through another slideshow. So what is open storage? This thing that we've been talking about. It's actually something we've been working on for a while. And John Fowler, our EVP of Systems, has, I think, the best nutshell description, which is, you all remember what Linux and x86 did to the server market around 2000. We're about to do the same thing for the storage market. So let me just explain what that means. If you think back to late 80s, early 90s, the server market consisted of a number of different leading vendors, each of which was pushing their own proprietary line of chips. HP had PA RISC, we had SPARC, IBM had Power. Actually, they didn't have Power yet, or there was one before that? I forget. And SGI had their MIPS-based hardware. There were a lot of folks competing. And all these architectures were different. Everyone had their own flavor of Unix. That was all different. And all these machines were relatively expensive. It was a nice high-margin business. What happened toward the end of the 90s is that the capabilities of x86 hardware got so competitive with all of the RISC architectures that it got to the point where people looked at this and said, you know, I'm accustomed to thinking I'm going to buy one of these RISC architectures in a standard Unix operating system, but I look at the cost and I look at the performance, and it's actually gotten to the point where the x86 machines are faster and they cost less, and there's this OS I can get over here that's free, and maybe that collection isn't quite as good as what I've got, maybe it's not quite as reliable, but it's good enough, and at 1/10 the price, I'll take the gamble. We see the same thing now happening with storage, in that you look at where the margins are in the IT world today, and really all of those margins are in storage. That's why there are so many players there. That's why so many startups are in the storage space. You don't see server startups very much because the margins more or less been squeezed out of that. Storage startups are everywhere. And the reason is that the leading players in that space are raking in tons of cash on the same model that server vendors did 10 or 15 years ago. The disruptive thing that we're doing is we are taking commodity hardware and open source software and providing a level of capability that was formerly not available except at a very high price. And when you take a zero off the price tag, we have found consistently that's sufficient to change the conversation. A couple things are making this possible. One of them is that if you were to look at the performance trends in CPU and memory and disk over the last 10 or 15 years, there's been an interesting thing that's happened, which is, actually I don't need a graph for this, but if you look at the performance in disk, and this is a roughly 10 to 15-year window. If you look at disk versus memory versus CPU, what's happened in performance for these devices? Disks are roughly 10x faster today than they were before. The IOPS are actually still not that much better, but because of the improvements in density and the fact that with rotational speed, the bandwidth goes up as the square root of the density because it's a area relationship. We've gotten roughly a 10x improvement in bandwidth. Memory, we've got roughly 100x improvement, and CPU, amazingly enough, about 1,000x improvement in CPU speed, right? Because we're hovering around the low gigahertz range today. If you were to go back, say, 15 years, you were more in the low megahertz range. Now, what does this mean? It means that computing systems collectively have gotten faster over the years, but the ratio between components has gotten skewed far off from what it used to be. And this has implications for the way we design things. One example being, it used to be an absolute rule when you were designing a storage system that thou shalt not use bcopy, meaning don't do copies of data from one place to another, don't make a pass over the data. Having 0 copies was always a very important thing to do. Why? Because your disk was delivering maybe something on the order of 10 megabytes a second, and your memory could handle maybe 50 megabytes a second, and your CPU could barely keep up with churning that. So if you had a checksum of the data or RAID parity computations to do, you were just no way going to be able to saturate the I/O channels. Compare that to now, where CPUs have gotten to the point where a single AMD core, for example, can do the XOR calculation for RAID parity at about 6 gigabytes a second. That's an enormous rate, and that's just a single core, right? You need an enormous I/O subsystem to be able to do a 6 gigabyte sustained. And of course, we're also going to multiple cores, which gets us to the other interesting trend line. If you look at what's happened with CPU, you might extrapolate from this that this trend is only going to amplify further. And that's kind of true. But if I take a look at, say, 82 to 87, 92, 97, 02, 07, well, I'm going 5-year increments starting back in the late 80s. Where were we in 1982? Right. Everybody remembers this number if you're of a certain age. Right? 4.77 megahertz, right? The original IBM PC.
Right.
That'd be a great Jeopardy question. What is we're actually just 4.77 megahertz?
What was the size of the first disk?
Yeah, that's right. Yeah, one of the things we often joke about is that it'd be fun to have what we call integer Jeopardy, right? Which is where you just name some hexadecimal integer and see if other engineers around the room can get it. So it's like 0xFBD0000. Oh, whoa, what is the start of OBP large mappings on Sun 4C? You know.
That's what we're going to be doing at the bar later.
Yeah, that's
That's
that's the game.
You go get
Yeah.
to go toe to toe with Jeff and I.
Yeah. So the fun thing that's happened is this, and I'll make this be a log scale, and you know that it's a logarithmic scale because I just wrote log here. If you take from the 4.77 megahertz to, we'll call current chip speeds, I'll call it 2 dot something gigahertz. It's in the 2 to 3 range. The interesting thing that happened is that we were on, I don't have all the data points at hand at the moment, but we were on a super exponential curve. So in other words, if this were a flat line, that would be exponential because it's a log scale. It was actually going up even faster than exponential. And starting in about 2002, that's where we got to the low gigahertz threshold. The first gigahertz chip was right around turn of the millennium. And the thing that's happened since then is this. It's actually stayed flat. And the reason is that there are limits to what we can do with CPU performance. And all of the effort, instead of being directed at higher clock rates, has been directed at having more cores. And you might ask, well, why are we doing that? Where's my Moore's law at? Well, Moore's law, of course, was always actually not about clock rate, but about number of transistors you can squeeze on a die. And the thing that happened with clock rate is that, just a little piece of trivia, 1 nanosecond is about 1 light foot, right? So the nanosecond is the time it takes light to travel this far, okay? So if you have a 2 gigahertz processor, that's 6 light inches, right, from one clock cycle to the next. And electricity doesn't actually travel as fast as light. It goes at a slower rate through different kinds of materials. So now you're talking maybe about, you got this much distance. And on a die that's a couple centimeters on a side, you're really at the limits of your ability to distribute clock. That's actually the fundamental limit. And that's why you're not going to see microprocessors getting much faster anytime soon. But we're still getting all these extra transistors. So the first thing that we did, and actually kept things going for a little while here, is just put more and more of them into onboard cache. Because after all, if the CPU is getting exponentially faster at a faster rate than memory, then every time you go to do a load from memory, that slows you down. So what you want to do is keep things close to the CPU. That's why we invested transistors in cache. But again, that's one of those exponentially tailing off things. Get to the point where you've got an 8 or 16 meg cache, you've pretty much exhausted the wins you're going to get from that. And at some point, somebody had the bright idea of saying, you know, if I've got a die that, here's my CPU die, and most of this real estate is cached, and over here I've got an LSU, and here I've got an ALU, and a couple other things. I said, gee, this stuff that actually does the computing is about 3% of the die. Why don't I maybe make the cache ever so slightly smaller and have 2 cores, or 4, or 8, which of course is where everybody is headed now. There's an interesting little problem though with going with multiple cores rather than a faster clock. And that's that your software must fundamentally be multi-threaded to take advantage of it. And this is where we think we have an enormous advantage. During this window of time, from about 92 to 02, 2 things were happening in parallel. One thing that was happening is that we were developing symmetric multiprocessing machines. We were a leader in that field, and by the time we had gotten toward the end of that decade, we had things scaling to 64-way machines. And of course, the advent of the Linux on x86 revolution, everyone sort of assumed those machines were dead, that architecture didn't matter, and everybody was just going to have 1U rack servers and scale horizontally, end of story. What's actually happened is that we now have both horizontal and vertical scaling. Because once you start talking about having, say, 4 to 8, and Intel already has an 80-core processor in the lab, so we're going to be seeing many, many more cores. When you start talking about having, pick a number, 64 cores on a die, you're back to having a really big symmetric multiprocessing problem. Even if these chips are going into 1U servers and you have racks of them that you're scaling horizontally, you still have, inside each box, a vertical scaling problem. So all the work that we did that got us to those big SMP machines, we may not be making machines quite like that anymore, but we are still running heavily threaded software. And the Solaris operating system has been heavily optimized for this over the course of about 15 years. It's an enormous amount of work, and it's not something anybody else is going to catch up to anytime soon. That was event number 1. Event number 2 that happened during this period of time is that this is when the storage industry, as we understand it today, came of age. This is when EMC and NetApp and all the players you're accustomed to thinking of as the biggest in the storage industry, this is when they went from being someone you barely ever heard of to a really titanic force. And what was happening during this period of time? CPU clock rate was growing as fast as it's ever grown. We went from, in the course of a single decade, from 92 to 02, this was the fastest period of growth in clock rate ever, even faster than the early 80s. We went from about 20 megahertz at the start of the 90s to 2 gigahertz at the end. So a factor of 100 improvement in CPU speed. That drove a set of decisions that is affecting the market today. It drove people to believe that the CPU will always get faster, the single-threaded performance of a CPU will always get faster than the storage subsystem. NetApp assumed that, EMC assumed that, and if you look at, for example, NetApp's data on tap operating system, it's fundamentally not multi-threaded. It's a fundamentally, at best, 2-threaded model, sort of a push-pull model with a work pile. And that's why they've been pushing so hard for things like, remember the DAS protocol they tried to introduce 4 or 5 years ago. It didn't really go anywhere, but the idea was offload as much from the CPU as possible, because the thing that NetApp filers are out of constantly is CPU. And the reason is, they didn't see this cliff coming. They didn't see that CPU performance all of a sudden was going to flat out stop, and meanwhile, trends in the density of storage, nobody saw, A, that because density was not actually going to hit a limit nearly as soon as they thought it was going to because of thanks to perpendicular reporting. We've got more density, more bandwidth. And the other is because of flash, we're now looking at machines that instead of doing on the order of hundreds of IOPS, are going to be capable of on the order of millions of IOPS. And of course, if you want to be able to service millions of IOPS, you've got to have a lot of CPU power, and you've got to be able to do it in parallel. So,
And one
yeah.
kind of dovetail what Jeff's saying. I think just one interesting experiment you can do, even before we even talk about what Sun's products are, is if you another sort of actual graph you can draw is if you just take the volume compute space as we define it today, and you take the storage space and pick basically any vendor like GE, NetApp, EMC, pick anyone, and you just look at what does a 2U controller get you. Right? So if you buy a box which is a 2U to 3U box, like a NetApp 3000 series or an EMC, NS60 or an S80, and you look at and then compare that to something like an HP, a Sun, Dell, IBM commodity compute server. Basically, in the storage space, a 2 to 3U box will get you, if you're lucky, 2 cores of CPU, about 4 to 8 gigabytes of RAM, and that will cost you about $50,000. And that same form factor in the commodity compute space, because of the changes that Jeff's talking about, today will get you 8 cores, so a factor of 4. It will get you probably 64, or in some cases more like 120 gigs of DRAM, right? And it will cost you about $12,000 to $15,000. So the really visceral evidence for what Jeff is talking about in the storage space is, right, in our volume space, what we expect is what it means to be in the commodity compute space is things double every 18 months, right? That's just how we define it, and Jeff is telling all about that. What we're seeing is that volume compute space is just accelerating away from the storage space to the point where you're 4 or 8x up in actual value, processing value, what you're getting, because there are software that allowing them to take advantage of that doubling curve. And that's really this is the first big transformation of open storage. What is the storage architecture? Because the actual we're talking about could actually take advantage of that economic weight behind it in the way that we built this.
Yeah, I mean, you guys have been talking about that for a while, so why haven't we seen that in the last year?
No one has yet released any products to do that. So that's one of the reasons we're starting to talk to you guys today is we're going to be launching our first actual enterprise class realizations of these things this year. There are people who are achieving those things today by leveraging CFS and Open Solaris, but because that's still sort of a model of sort of self-assembly, and that's in fact what our customers here today is doing, right? You're actually gaining those advantages, but you're still having to do a lot of things yourself. And actually, we were talking about that before in terms of the kinds of things that CFS is giving you a lot, but there are other things you have to do for yourself because it's still a system administrator who's a server administrator is putting those pieces together. What we're going to do is release products that have the feature set that you would traditionally classify as an enterprise class storage product, but with the same architectural properties that Jeff is talking about to take advantage of that.
I mean, if this was so obvious, and like you said, there's so many storage startups, and you know how the Valley works. I mean, why wouldn't somebody else have jumped on this ideas?
That's a really big question. A bunch of storage. I mean, they're actually is that storage business is a truck business, and so if you want to the storage sort of comes along and has just started the example you wrap server. Right? Well, that's a commodity. So you're right.
And
because it's a commodity, and really when you're buying one you compute for, you're not actually buying when you serve a credit card, it's Linux compute cycles. So if your box doesn't buy my Linux compute cycles from somebody else, data is perfect because my company's going to be around in 5 years. My data needs to be around in 5 years. Can I get my data back, right? Or, is my machine going to be able to do that? So I think that is one of the things that has inhibited startups is sort of the trust thing. And you have to have the brand reputation, and you have to believe that the company understands how to service products in the enterprise. So that's one issue. The other issue is, I think you can flip it around and ask the question, why haven't the established players done that? And that's where we get into the software part. Just to pick on one example, if you look at, say, EMC. So what's EMC's operating system? Well, currently it's, on some of their products, one microkernel that they wrote 15 years ago. That's Dart. On another set of products, a different real-time microkernel that they wrote 15 years ago. That's Flare. Then there's the machines that are running the Windows NT kernel that they're licensing from Microsoft. And the fourth operating system is that they're paying Red Hat to give them a copy of Linux that they then hack up with some other software. So you sort of look at that and say, okay, very successful company sort of this huge product portfolio, but where is the place where there's of the four things I just named, where are you going to invest your software dollars to do the kinds of core things that you have to do to scale with that? And it's very unclear. Right? And again, there's a lot of good things about their product portfolio, but core OS investment to scale is certainly not one of them. And that's very, in sort of one very visceral illustration of what I'm talking about is, if you look at, like, in their NAS line, if you just look at the controllers, they have the NS20, the NS40, the NS60, the NS80, right? So you see all these things go like this, except for memory. If you look at memory, it's 4 gigabytes, 4 gigabytes, 4 gigabytes, 4 gigabytes. And what does that number mean to us? It's like, that's how much memory a 32-bit kernel can support. They can't have more memory in it because they'd have to rewrite, in the middle of rewriting their kernel to be 64 bits, something that Linux and Solaris and other operating systems did that 8 years ago, right? So, I think that's one of the reasons why, not to say that I think it would be very inappropriate to say that no one else can do it, but I think our perception is there's a window of time here where no one's startup has been successful because of some of the inhibitors to that. At the same time, the entrenched competitors and their entrenched success have not been able to get over the barrier to go do some of those things. Yes, sir?
Well, since you used the example of EMC, which uses Red Hat, why couldn't they partner with Red Hat, use the Red Hat extended file system and 64-bit, make it a partnership?
Well, I think they could, and they have licensed that, but I think the issue there is what's the development model and what assets do they have versus what's going to Linux community. There's a lot of sort of mismatches there, right? If you ask them, they would say RAID and file systems, and they're an extremely proprietary company. Jeff, I don't know if you want to add to that.
Just the idea of Linux as a storage system is really, it leaves a lot to be desired, right? Because exe3 or exe4 as a file system still fundamentally is not transactional. It doesn't survive power failure. It has the semantic that you run the risk of either A, losing data, or B, having a recovery time that could be measured in hours or in days. So just the fact that storage capacity has grown so much has two really big implications. One is that you actually have to transition to transactional software, just as databases did 2 or 3 decades ago, because there's no other way to keep the data online at the rate that at the frequency that you need, or the percentage availability that you need. The other is that there are a lot of implications to servicing really huge quantities of storage that are not necessarily immediately obvious. Like, for example, almost every file system out there today, other than ZFS, has what's called a bitmap to keep track of its notion of which blocks are free and which are allocated. And the only way that a bitmap actually works efficiently is because it's 1 bit per block. It only really works efficiently if you can store the entire bitmap in memory. Because you have to read and write that thing from disk all the time, it ends up being really expensive. And when the ratio between CPU and memory, between memory and disk wasn't quite so large, it was less of a problem. This 10x here, of course, is a performance number. The capacity number is vastly different. The capacity number on disk is more like 1000x, because we've gone from gigabyte drives to terabyte drives in the course of a decade. So disk capacity versus memory capacity has been growing much faster. And what that means is that the memory structures that you need to represent what's on disk, they don't really fit anymore for traditional file system designs. So we have a very different approach to that in ZFS, because we went into it from the beginning saying, what happens if we have to manage routinely petabytes, exabytes, zettabytes of data? How are we going to handle that? How do we design algorithms that scale to that level? One thing we realized first was that you had to be transactional, because the idea of scanning the entire file system to do really anything is just not feasible. It'll just take too long. It's kind of like one of the key enabling technologies. We build inside of the Sun. We have the source code for Solaris, and we have a standard place where we put changes to it. And once every night, we do what we call a nightly build, which is where a compiler runs off and it builds all the source code and produces fresh packages that we can all go off and install. And the key enabling technology for our nightly builds was getting machines fast enough that you could build in less than 24 hours. Right? Because we used to have weekly builds, because there was a time when building took like 3 or 4 days back in the early 90s. And similarly, when you look at the time that it takes to do an operation like a file system check, if the time between crashes is measured in months and the time to FSCK is measured in months, well, clearly you've got a serious uptime problem. There's another one, though, that's a little bit less obvious, which is you would think that the error rates in disk drives would be, I'm not sure what you would think. Ooh, someone's a permanent marker. Oh. That's not nice. All right, deal with that later.
Yeah, we'll get that later.
File a bug. So the error rate for disk drives is typically advertised as about 10 to the minus 14, or in other words, one bad bit per 10 to the 14th bits transferred for desktop class drives, and 10 to the minus 15 for enterprise class drives. There have been a couple of studies that have come out just in the last couple of years. You've probably seen them. One was done by Google. There was another that was done, because they just have a ton of disk drives laying around. There was another one that was done by Carnegie Mellon. And there's a third, I'll describe in a little bit more detail in a second, that was done by CERN. What they all found is that, in fact, this 10 to the minus 15, that doesn't ever actually happen. The 10 to the minus 14 is actually about what you get, which works out to, this is roughly 8 terabytes. So in other words, if you go and just read 8 terabytes of data, you're going to get, typically, one bad read among that bunch. Now, 8 terabytes, there was a point in time, right, 10 years ago, where you'd say 8 terabytes, that's such an enormous quantity, my odds are pretty good of not having an error. Of course, now, 8 terabytes is just 8 disk drives worth of data, right? So getting data corruption as part of daily life is actually something that we really have to deal with. And that it's something that you can't sort of bolt on after the fact. It's got to be integral to the file system. So one of the things we did in ZFS is make sure that all the data that we have is checksummed. And the key, too, look at that, is that instead of doing the usual sort of EMC type trick of having, instead of 512 byte sectors, they have 520 byte sectors, and there's checksum information here. The problem with that, of course, is that if there's a bad bit here in the data, your checksum will catch that that's a wrong bit. But if, on the other hand, you simply failed to write the sector entirely, and this actually happens because you get what's called high-flying writes, which is where the disk head floats above the surface of the platter on an air cushion. And it actually, of course, there's vibration, and it moves up and down a bit. And you need to make sure it doesn't get too close to the platter, because if it makes contact, that's a head crash, and that's going to be a disaster. But you also have a problem making sure it doesn't get too high, because if it does, then there won't be enough field strength to actually magnetize the bits underneath. When that happens, it's called the high flying right. And what happens is none of these bits end up getting written. And when that happens, you come back to read this block later. Well, the old checksum matches the old data that was in that block. So as far as you can tell, it's correct. That's obviously a bad thing. So what we did in ZFS is we actually borrowed a technique from cryptography and used something called a Merkle tree, which is, instead of having the checksums in the data blocks, we say, hey, look, we're a file system. We have to have a tree of blocks anyway. So in the block pointers that point to these data blocks, and of course it's a wider tree than I'm drawing, but this just fits on the...
So Jeff, this is within ZFS.
This is all just like what's inside of ZFS, inside the guts of it, is that each of our block pointers actually has a fair amount of information. It tells you, which disk and which offset on that disk you're supposed to look at. It also tells you what the checksum is of the data, so that when I am reading this block, I'm not comparing it against itself. I'm comparing it against an external piece of information. And I know that that checksum is correct, because it in turn was checksummed by the block above that, and so on all the way up to the top. So you have an entire tree that is self-validating. And if you make this a cryptographic checksum, then in addition to making it self-validating, it also makes it tamper-proof, because you can't modify any block in the system without inducing a checksum error or changing the checksum at the root of the tree, which is kind of a handy property for physical migration of storage.
So the thing that's really important about this, because we were talking earlier about the economics, right, is this is one example of an innovation that Jeff has done in ZFS layer, which is basically giving you the next generation of enterprise class reliability by an innovation in the software stack and building that on top of the commodity disk drive, right? And that's really why this is valuable. And there are many other examples we could go into, but this is just to give you a flavor of this sort of idea that, what people have done, and so one study that you guys probably all familiar with, right, is the Google did study of disk drives, right? And so all the disk drive vendors have, my laptop class line, my enterprise class line, above, right, all the things you would expect. And of course, the price just goes up and up and up, right? And so Google did a really interesting study, and this was independently confirmed. I think it was by Carnegie Mellon or some other folks published it before. Basically said, actually we took all these disk drives and we measured them. We looked at the smart data, and we talked about that earlier, and said, actually there's not much difference, right, in terms of the quality that we were experiencing for disk drives. And so that's really interesting, because it means that, right, there's been this big realization out there in the customer base already, which is, I want to build my storage, and I want the unit of capacity to be a cheap SATA commodity disk drive. However, I am not willing, for my business purposes, to give up all of the enterprise features that I expect out of my storage. And obviously, a primary one of those is it has to stay up all the time. It has to have the reliability attributes that I'm looking for. So this is an example of innovation in software that actually has a specific economic purpose in open storage, which is using that commodity component and then being able to get that stuff. And I think that's sort of started this out talking about what is open storage, right? And so obviously one part is, okay, it's open. ZFS is open source. The protocols are open. That's something anyone can claim. But actually the source is open. The data formats are open, right? So you have investment protection of your data. That's one part. Other part is this commodity economics and leveraging that. And the third part is innovations, right? Things about what Jeff's talking about. And those innovations that we're doing are really, some of them are unique in the industry, like we're talking about with Flash, but others are just in order to enable us to give you an enterprise class storage solution built out of commodity components. Right.
So I think with that, let's have spend some time just tying this all together, hearing Mark give us an overview of how it is that you're using Open Solaris. I mean, you can sit down if you want, if you want to stand up, whatever's easier for you.
Sure. So I'm with RStage.com. RStage.com is a music discovery site. I'll try not to use it.
Not permanent.
Not the permanent one.
Don't use it permanent.
Cool.
The red one's permanent.
RStage.com is a music discovery site.
Oh, mind your way.
And it's a place where fans of music come to and find new music to listen to. And artists being anyone who can create music, anyway from working on their Mac with a MIDI system in their bedroom to the bands that have already put out albums can upload their music. And we're very different than somebody like Gracenote or Pandora in that we've really built a community around it, and we allow people to discover new music. So where that ties with open storage, and I'll use kind of a timeline here, Jeff's cue. We're almost 2 years old now. We formed the company, I think it was in October of 2006, and I was brought on board in January of 2007. We launched in March 1st, 2007. So I'd only been with the company about a month and a half when we went live. So we really built a production site, a production website, in about a month and a half. You know, the physical piece of it. Because it happened so fast, the real challenge was, you know, what can we pull together in that timeline? And it was built by two people, our VP of Operations, Dick Pascal, and myself. And it was really a matter of what pieces are we familiar with, and what are the known quantities that we know that we can use today without making a big science project of it. That's always our goal on the hardware side, is avoid all the science projects, and so we deploy quickly. So we went with commodity hardware, and we both used recent vintage commodity hardware from Tyan and Supermicro. Similar quality to what we expect from somebody like Dell. And we use CentOS, which is a open source distribution of Red Hat Enterprise. So very well known quantities, ton of information out there. I know that if I run into a problem with a kernel or with smart data information, I can go to the web, simple Google search and find an answer. And that's really what we built the site out of. On the storage side, we're collecting a lot of music. I mean, we now have somewhere north of 50,000 artists have uploaded their music, and so the number of songs are 50,000 times, 4 or 5 or more, and it's rolling in all the time. Every month we run a contest, so it's an ever-growing, and if the company's successful, that's going to happen. So our storage needs are going to grow, and it's a matter of how fast. So our original storage was CentOS, served via NFS with an iSCSI backend. We're actually using a kind of a third-party iSCSI vendor, and that worked really well for about 6 months. At that point, we didn't run out of storage capacity, but we did start to run out of performance. And we ran out of performance both on the iSCSI side and on NFS. NFS being actually the bigger problem. So we spent a couple of months, trying to dig into what the problem was. And one of the strengths and weaknesses of Linux is you've got a lot of tools to work with, but they don't necessarily work together. So we spent a lot of time, really trying to diagnose, where this problem coming out of? Because we had several things in the stack. We had NFS serving the clients. We had the iSCSI connection to our SAN, and then XFS on the SAN itself. And it turned into a science project. And the biggest problem there was twofold. It was the amount of information available to really scale Linux. Because if you want to scale Linux, you're going to have to do a lot of the work yourself. It doesn't come out of the box tuned for your hardware. And oftentimes it doesn't for modern hardware. The other thing you're going to have to do is figure out which tools you need. I mean, you've got a problem of tool integration. So there's one set of diagnostics procedures and tools to work with NFS, a different one for iSCSI, and yet again for XFS. It's at that point we had been able to tune for a few months, but we really knew this was diminishing returns, and there was a point at which we really needed a new solution. And that's when we started looking at various vendors. Do we buy storage from somebody like NetApp? Do we buy storage from somebody like Sun? And it was about that time that we became aware of the Open Solaris project. And so as a little bit of a research project, we put together a prototype system. It's all, again, we built a lot of commodity hardware. We know the vendors that we have. We know the quality of what we're getting. We know that we're going to get the back end support from them. And we built up an Open Solaris system based on ZFS. And right away, our first impression was we're impressed with the integration. Just the fact that there was one tool set and that was designed to work with one operating system and one source of information. That was a huge benefit, just off the top. Because again, we weren't guessing. We also found when we started testing, we were getting throughput, big throughput improvements. And this was just on a test system. At that point, we were late fall, early winter last year. And we decided to go ahead and just build that system as a production system and try it out. That went well, and right now all of our storage has been converted over to ZFS. We've got 4 storage servers, the kind of the story behind the hardware we choose is kind of interesting. We, again, with our Linux background, we're really keen to avoid driver problems. And we're using commodity hardware, and with Linux, there's a lot of driver support, but it's possible to get in these kind of combinations that becomes a science project. You've got to make the parts fit together. So we actually went to the specs on Thumper and said, what chipsets does Sun support? And you guys have done the hard work here. Let's get the laundry list. With that, we went to the Supermicro catalog and said, well, there's the Marvell chip that Sun seems to like and is well supported. And there's the front side bus. And it turns out they have a number of systems that it comes right down to it, turn out to be about a third of a Thumper. So we kind of like to think of the hardware we build as 1/3 of a Thumper. It has its limitations. We know we can test for that now. We've got the tool set to be able to test for that. So now, instead of knowing we have a problem when it shows up, it's something we can start to anticipate, and we've got a plan to be able to deal with it. But it's been a real success story for us. And as I was telling Jeff earlier today, the key for us really is the integration. The fact that it is one tool set, it's designed to work together, and it comes from a trusted vendor. Mike's point, that trust is significant. And I think it was that trust that allowed us to make the leap from it's something that works in the lab to what's the point of spending a lot of time looking at a lot of different vendors. Let's go with this known package. We've got the backing of some, and that's where we are today. Yes.
So why didn't you buy a company? What was the price differential?
We're a startup. We don't have a lot of money, and frankly, that was a much bigger box than we really needed from day one. So when I say we're building a third of the Thumper, we've got 16 bay boxes with 1 terabyte drives, as opposed to a 48 bay box.
Oh, sorry, you have 16, what was that?
So we have 16 bay boxes, so there's 16 drives per each of our storage units. So we're scaling on our rate of increase of storage is smaller than, say, a Thumper would provide us. That would be a much bigger step. And we're not really there today.
So I have a question. So going forward, what is your, do you think that your storage, needs or how you're going to address it, is that going to change? And if so, how do you anticipate getting ahead of that?
It's clearly going to grow. I mean, we expect to be pulling more of these kinds of boxes. The sophistication of how we use it will change. I mean, right now our storage problem is replication. So we've got 4 of these boxes. One of them holds our original media. So we really have multiple copies of each artist's song. We've got the original media they uploaded, and that can be any one of 12.5 different audio formats. We've got, and then a couple different transcoded versions of it. One which plays on the site, and then a third one which you can download if you want to purchase the song, or we have an iPhone app as well. So if you have an iPhone, you can listen on the site. So the original media is kind of, to us, those are the crown jewels. We need to keep that around. You never know what we might go to in the future. So we've got 2 copies of that. Keeping that in sync right now, it works. We're using our sync, but I know there's something better. There's going to be something better.
Yeah, ZFS send receive is real handy for keeping things in sync.
Yeah, and that's something we've fiddled around with a little bit. We don't really have working quite yet. It has a lot to do with the way the 2 colos are set up.
Oh, okay.
Yeah.
So you want to actually
it's a
boost
network
your
problem.
synchronization.
Yes. Yeah. So it's a networking problem at this stage. Yes.
From a technology perspective, I think the reasons behind the selection I think are pretty clear. Obviously, I think there's different choices being made every stage along the way. But besides the pure technology perspective, in terms of some of the ancillary factors, in terms of, for example, getting resources, to work on the architecture as it scales out, to possibly move pieces of it to a cloud environment, and then now you potentially have a technology disconnect going back and forth. How does that factor in? In other words, on a standalone basis, okay, it's a good solution, but in terms of how you build out and potentially how you expand beyond the boundaries of just your organization, have you thought through some implications of what you built out right now?
Every week. I mean, that was actually a decision, in the beginning. Do we build our own colos? So we own our own colos, completely built out by ourselves. From the hardware, networking, and then we could have gone that route. We could have gone hosting. We could have gone cloud computing. And we've stuck with the colo for two reasons. One of it is very situational. Our VP of operations and myself are very technical guys. I'm actually an ex-developer, or on vacation from developing. And so it's the kind of thing that was very easy and very natural for us to tackle on our own. He's worked with hosting environments before, and there's trade-offs. There's trade-offs in situations. And it was really a confidence in ourselves to go off and do this. It has paid off, but it's not for everybody. And Mike was talking about, can you go out and build? You can go out and build, something like Fishworks. I'm presupposing what some of the details. But you can go out, build the pieces now, and I think that's a lot of what we have today.
Right.
Well, again, that was a decision that was made based upon our confidence in our technical ability. It's not for everybody, and that has a lot to do with the number of different pieces that have to be integrated, pulled together, and you have to understand. So it's a couple things. You have to make the decision based on your capability of your organization, but also there's a matter of growth. And when we started, there was a tremendous black hole of projections of how fast we would grow, and we're really concerned about overwhelming whatever option we wanted.
I have one question for you, which is the flip side of, we talked about picking your things, but is it correct that the reason you decided initially, just with a blank piece of paper, to look towards the model you look towards versus, say, just buying an NetApp filer or an EMC box or whatever, was purely because of price performance of that, in terms of just like, it just costs too much and that's why you started?
Yes.
Okay.
Yes. Yeah, we're a very small startup. As I say, there's only 3 of us in the operations group, and there's 9 developers, and budgets are commensurate with that. So, really, you're going with that going with a NetApp filer from day one would have been a big purchase decision for us. That's changed. I mean, if we were to do it with today's budgets, we have many more options. But frankly, we're down a path that works.
And you think that there's room for growth as well?
With the solution, with the solution path we're on today, absolutely. The limitation, and this is something that, working on 2 years in now, we kind of have the luxury of sitting down and thinking about. The limitation is going to be on the commodity hardware itself, right? So I can choose all the chipsets, but I can't choose the way they're put together. And the big thing we see now is there are measurable I/O bandwidth limits within some of the hardware we're using. Right? So it's great to have the right set of AMD front bus chips and the right set of Marvell disk controllers. But if you only have half or a third the number of I/O channels between them, you're going to run into the same kind of limitations you were talking about. And that will be our limitation. And that's also the reason we have, it's another reason we have 16-bay boxes as opposed to something else. We've estimated that that's probably a realistic limit to a balance. And it's a question of balance between storage volume, how we're going to use that storage, and what the box can pump out.
Are your storage servers just storage and file servers, or are you running applications on them as well?
We are not. So actually, I say budget is very significant for us, but we're also very, very modular. So storage is just storage. Application server is just application server. Database, likewise.
Do you guys ever consider maybe doing that way, so you don't have one stack of hardware and use virtualization?
No, because again, there's only 3 of us, and we like to sleep. And we're very big on making sure that when one thing breaks, it doesn't break 3 others. So we put a tremendous amount of effort into that.
Well, that's a good segue, actually. I think we wanted to, we'll have a chance to ask Mark questions, at the end. I wanted Mike to go and give us an overview of a project that he's been working on, kind of a